This video is a combination of many of the fundamental and classical machine learning and deep learning concepts video that I did previously in my channel, with the addition of few more that was not there in the previous videos. And almost all of these concepts are super popular in a data science interview situation in case you are preparing for one. So I hope that this will be useful to you. Why do we need a bias term in any machine learning algorithm such as linear regression or a neural network? Now, this is a classical representation of a linear regression equation where y is the dependent variable and a is the bias term. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. Now, the simple answer to that question is that bias in linear regression, that is this variable a here, is used to move the line, the prediction hyperplane line, up or down. What do I mean by this? That is, in linear regression, without the bias term, your solution has to go through the origin. That is, in this case, this green line is my solution line, that is a predicted line or the prediction line or hyperparameter, various ways it is called. And because there is no bias, when all the feature values are 0, then the prediction also needs to be 0. And here features are just two-dimensional features, that is x and y. Now, this situation, that is this constraint, that is the prediction needs to be 0 when x and y is 0, may not be the answer of your training data set. That is, your training data may have a bias, which means that even if the features x and y values are 0, y is not 0. So how do I capture that characteristic of the training data set? And that's by using the bias term. So the goal of linear regression is to estimate the parameters that best predict the outcome given the input features or the predictors. If the expected value of your outcome variable is not 0, then we would also need to estimate the bias weight along with the feature weights. And if we do not account for this bias, then the prediction from your estimated model will be very off. So adding a bias weight that does not depend on any of the features allows the hyperplane described by your learned weights to more easily fit data, that is, fit the training data that does not pass through the origin. And that's how we add a bias term, which is what is represented in the image on the right side here. Even when x and y is 0, that is at this point, that is all the features of the prediction model are 0, the predicted value is not 0. And now let's see the case for a neural network. So a bias value in a neural network allows you to shift the activation function to the left or right, which may be critical for your successful learning. And what do I mean by that? Let's check out this simple example here. Consider this one input, one output network that has no bias. So in this case, the output of the network is computed by multiplying the input x by the weight w0 and passing the result through some kind of activation function, for example, a sigmoid function. And on the right bottom side, we see the graphical representation of the function, where in the x-axis we present the input value, and the y-axis presents the output value. And the graph very much shows the various values that w0 can take and how that affects the final output. For example, if I give 0.5 or 1 or 2 as the weight values, then that's how the curve changes. And effectively what's happening is that by changing the values of the weight, I'm affecting the overall steepness of the curve. But what if I want the output value to be 0 when x is 2? Then just changing the weight to take different values does not help me. So in that case, what is needed is you want to be able to shift the entire curve to the right. And that's exactly the bias term will allow you to do, like so. So here in this situation, now I am adding a bias term here with a value of 1. So in that case, the output of the network becomes the weighted sum of these two factors. That is, the output will be w0 into x plus w1 times 1, and take the whole weighted sum you supply to the sigmoid function, and that's my output. And by doing that, here is the final result. That is the same curve what I'm getting with the bias term. And now we can see that with the weight of -5 here for w1, that will shift the curve to the right, which allows us to have a network that outputs 0 when x is 2, which is exactly what we wanted. So overall, a layer in a neural network without a bias is nothing more than a multiplication of the input vector with a matrix. This means that you are using a linear function, and thus an input of all zeros will always be mapped to an output of all zeros. This might be a reasonable solution for some system or some training data set, but in general, it is too restrictive. Hence, using or adding a bias term, you are effectively adding another dimension to your input space. So you are avoiding an input vector of all zeros. And modification of the neuron weights alone only serves to manipulate the shape or curvature of your transfer function and not its equilibrium or zero crossing point. That's exactly what we saw in this. That is, here I was able to control only the steepness of this curvature, but not the positioning, and I was not able to shift this curve altogether at all. But with the bias term, I can shift the curve. So that's exactly what your bias term will allow you to do. That it will introduce the introduction of the bias neuron will allow you to shift the transfer function curve horizontally, that is left or right, along the input axis, while leaving the shape or curvature unaltered. This will allow the network to produce arbitrary outputs different from the defaults, and hence you can customize or shift the input to output mapping to suit your particular needs. So a common fundamental question that is asked in many data science interviews, that how do you calculate the number of parameters of an MLP neural network? And MLP here obviously stands for multi-layer perceptron. Now let's take a look at this architecture. It has 4 neurons in the input layer, 5 neurons in its single hidden layer, and 1 output layer. As seen in the figure, all of the input neurons are mapped to all of the hidden layer neurons. That is, it is a fully connected network here. And suppose each neurons in the hidden layer has a bias associated with it. Furthermore, each neuron from hidden layer is mapped to a single output layer. Suppose the output layer also has a bias, and each of these connected path has some weights. So now let's try to find out the number of parameters to be learned. And here is the answer. So number of input at here in this layer, number of inputs into number of neurons in this first layer is 4 into 5. Then the number of weights between the hidden layer and output layer would be number of neurons in the hidden layer into number of neurons in the output layer, which is 5 into 1. And also we have this number of biases to consider, and in the hidden layer I have 5 neurons and 5 bias, so that becomes my 5 here. And finally, the number of biases for the output layer is just 1, because it's a single neuron at the output layer. So the total number of parameters to be learned here will be 20 from here, plus 5 plus 5 plus 1, that is 31. Why does it take more time to maintain multiple instances of a relational database than a NoSQL database like MongoDB? So, a relational DBMS mainly promises consistency. When it's spread across multiple instances, it makes you wait until all or at least the majority of instances agree on the final state of the transaction. Thus, you buy the consistent state of the database for the time it takes for all the instances to come to an agreement about the transaction state. And a so-called NoSQL DBMS generally promises very short local response time at the price of not guaranteeing the same transaction state in its other instances at any point in time, which includes never in some cases. And this requirement of consistency of databases also differs based on the use case. For example, some applications, airline seat reservation, for example, value consistency more, while others might prefer faster response time, even if the result is not necessarily true, like some social network. So it completely depends on your specific use case. And a related question that may come to your mind is SQL Server or NoSQL more cost efficient when scaling horizontally? So the cost of horizontal scalability is mostly a function of hardware provisioning and server hosting, and much removed from the software used for a database system, in my opinion. Yes, NoSQL databases are meant to be able to horizontally scale more easily, but that does not necessarily mean more cheaply. Horizontal scaling typically involves multiple servers, which means more hardware provisioning, that is, disk memory and CPU all at once, than vertically scaling a single server, since usually further provisioning is needed as a result of not all resources being exhausted at one time, rather, a particular resource topping out instead. And hence, overall, you really have to know your requirement first and then decide on the kind of database you want to use in your particular case. Today in this video, I will go over the concepts of gram metrics. Probably you already know that gram metrics became very popular after neural style transfer came into the world, because gram metrics is what made possible for neural style transfer algorithm to be able to compare images, the styles of images, and ultimately transfer one style from one image to another image. All right, let's jump in. In simple words, a gram matrix is a matrix created by multiplying a matrix with its own transpose. As you can see in this image here, that consider a matrix V given as follows. V is 1, 2, 3, 4. It's a 2 square matrix of 2 rows, 2 column. Then the transpose of this matrix V transpose will be computed as just just transpose the rows and columns. So 1, 3 goes like this, and so it becomes 1, 3 here, and 2, 4 comes down, and that's what we have. So that becomes a transpose, and now the gram or the Gramian matrix G is calculated by checking the matrix product of the two matrices V and V transpose as follows. G equal to V transpose multiplied by V, and it's a dot product between these two matrices, and ultimately I get these result as 10, 14, 14, 20, and that's the gram matrix of these two matrices. But to understand gram matrix and how they capture the styles of an image, first we need to revisit the concept of dot product of two vectors. So here is that image. Let's take a note of this image, that we have A and B vectors here, and both of them are represented in a plane. Now, the more correlated A and B are, the more closer the vectors are. That is, the more similar they are, which also means if they are closer, the angle between them, the angle theta here, will be less. And by pure trigonometric rule, the less this angle theta, the more is a cosine of theta. That is more the value of the expression A dot B equal to A and modulus of A and modulus of B multiplied by cos theta. That's the dot product value of them. So less the theta, this expression will be more, because cos theta will be more. So ultimately more is the dot product between them. So with this thing and this expression, what we ultimately get is, the rule that we get is, when the dot product of two vectors are larger, then we can infer those two vectors are similar. Now, what does this theory of vector dot products have to do with a image-based neural network? And that's because when an image moves through the various layers of a neural network, the content of an image is represented by the values of the intermediate feature maps. These feature maps are all tensors, or you can say metrics, and it turns out the style of an image can be described by the means and correlations across the different feature maps. Now, for style extraction from your input images, we need to find the correlation between the features in each layer. But the question is, how do I find the correlation between these features? And the answer to that is Gram matrix. So here, Gram matrix is used to determine if two matrices, in this case filters, are correlated. It is achieved by calculating the dot product of the vectors of the two filters, and this matrix obtained with the dot product of the vectors is our Gram matrix. If the dot product across two filters is large, then the two are said to be correlated, and if it is small, then the images are uncorrelated, just as what we talked about in the previous layer. Now, consider an example. Consider two vectors, more specifically two flattened feature vector from a convolution feature map of depth C. So this is that tensor with a depth of C and width and height, representing the features of the input space. Now take all C feature vectors flattened from these. So again, these depth is represented, actually filled up by many features. So right now this pink slice is showing just one feature map, but there will be many feature maps here. So take all C feature vectors flattened from the convolution, from this convolutional feature map of depth C, and compute the dot product with every one of them, including with the feature vector itself. And the result is your Gram matrix of size C by C. This dot product of theirs gives us information about the relation between them. The lesser the product, the more different the learned features are, and greater the dot product, the more correlated the features are. In other words, the lesser the dot product, the lesser the two features co-occur, and the greater the dot product, the more they occur together. This, in a sense, gives information about an image style or its texture, and zero information about its spatial structure, since we already flattened the feature and performed dot product on top of it. Expanding on the same idea further, let's take a note of this figure here. So here in this image, I am representing the different channels of feature maps in a particular layer, in a specific layer I mean. So at this specific layer, each channel of this feature map represents the different features present in the image. Now, if we can anyhow find the correlation between these features, we can get the idea of the style, as a correlation is nothing but the co-occurrences of the image. So in this figure, we can see that we have a red channel, yellow channel, and green channel. And let's say the red channel and yellow channel are fired up with high activation values. That means they have high correlation, meaning they occur together. So these two channels will have a high correlation than that between red and green, and we know that these co-occurrences can be calculated by calculating the correlation. But we have to calculate this correlation between all the channels, all the feature maps, and that correlation between among all the channels with respect to each other is given by the Gram matrix of an image. Hence, we do calculate Gram matrix to measure the degree of correlation between channels, which later will act as a measure of the style itself. And now the exact process of calculating the Gram matrix, or the algorithm of calculating the Gram matrix. So take a look of this top part of the image. So here I have the input space of my input image, and this is a tensor of size h by w by c, and the c is the depth or the number of channels, and then I flatten it. So I become, one dimension becomes h into w, height into width, and another dimension remains C. That is this is the number of channels in the original input space. And when I calculate the gram matrix on these, the resultant gram matrix will be a C by C matrix. So this is the overall simple steps in a nutshell. And then take a look at this part of the image. Here it gives a little bit more on the actual implementation algorithm. So take a feature map fi of size w by w, then output will be a gram matrix in the space of n by n, and the step 1 would be for each feature map. So in our example, on the top part of the example, the original was h by w by c. That was the input space of the original tensor, and the gram matrix just becomes c by c. And here they are pretty much saying the same thing. That okay. So now in the step 1, for each feature map fi, vectorize fi in convolution layer into a one-dimensional vector. So that's what this step was doing in the top part of the image. And then combine. So after vectorizing, we will get quite a few L, that is each of them is flattened like this. And then step 2 is to combine n one-dimensional vector Li into a matrix F in the order of the feature maps. And the step 3, get the transposed matrix F transpose of matrix F and compute the gram matrix according to equation. Our equation 3 here, one second. Yeah, so this is that equation 3 that I'm talking about. That once we calculate the original, once we calculate the matrix F here and then take a transpose of F, then the gram matrix will simply become the dot product between them. So each element here, Mij in the gram matrix M, is the inner product of the fi and fj, which can be obtained with this expression. So this was very mathematically represented. So in more simpler term, say, so going back to our original algorithm here, in a simpler term, say you have a set of images and you want to calculate the gram matrix. So to start the process, say the image you have are of m by n shape. So first reshape a single one to m into n into 1, that is flatten the shape. That is, here we are just multiplying h by w. That's exactly what I'm talking about. And similarly, after doing for this single image, convert all other images to a same kind of flattened vector, and then from all those vector form a matrix, say m, and then the gram matrix G of those individual set of images will be the matrix that is obtained by from all these individual vectors and the transpose of that matrix. That is, here in this algorithm, f and ft, if you get the dot product of f and ft, that's simply your gram matrix. And following the same algorithm, a simple Python implementation is here. So look at the function. This gram matrix takes a tensor function to gram matrix from image tensor, right? And first, that what I was doing here, that I am unwrapping them to flatten them. So here exactly I'm doing that. First, I'm getting from the tensor.size, I'm getting their batch, then the height, width, and the distance, and then I'm doing tensor.view to flatten them, and the parameter passed are d and h into w. D is the depth and height and width. Then just simple matrix multiplication of these tensor and the transpose of this tensor. That is what we got here in this algorithm. F is a tensor, is a matrix that we got after flattening all individual ones, and then I take the transpose of ft as well, and then calculate the matrix multiplication of those. That is torch dot, here I am assuming that I'm using PyTorch, so torch.mm, and then I'm passing tensor and tensor.t, and that is very much my gram matrix, and that's what this function returns. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching. In this video, I will quickly implement dice coefficient from scratch. This is a very important metric when you are doing segmentation projects with a large set of images. So simply put, dice coefficient is pretty much this formula, which is 2 into the area of overlap divided by the total number of pixels in both images. And more mathematically, its expression is this, that is 2 into x intersection y divided by x summation y. So now I'm going to do the implementation. So in this cell, obviously all the regular imports and then the actual method. Dice coefficient y true and y. And I have to supply a parameter argument called smooth, which is like a very small number. For default value, I'm giving 1. And y true, y predict are just two sets of images. And when you are actually running batches in a deep neural network, then it will be a 4-dimensional tensor. The first dimension being the batch number of samples in a batch. Intersection will be k dot sum y true times y spread and smooth. I don't know, smooth. Axis will be equal to the second, third, and fourth axis. Because the first axis is a batch, so 1, 2, and 3. Because here in this method I am doing for a batch kind of setup, and not for two images individually. Union will be k dot sum y true, axis again will be 1, 2, 3. To that I have to add k dot sum y red. Yeah, it makes sense. Oh, y true, dear. Wait. Alright, I have the intersection and union, then just have to implement the formula, which is return value will be k dot mean uh, 2 into intersection plus smooth. You have to give this smooth value, don't forget that one. And division will be union plus smooth. Yep. Yeah, that's the I have to mention the axis over here, so that because now I will be summing over the first axis, that is a batch axis, so x is equal to 0. What is the problem with this? Another one here. Alright, now I have two images saved in my same directory, so let me bring that. Y predict equal to cv2 dot imread, and my image name is image underscore 1. So you can imagine this one actually represent the tensor representing the true values, and I have to normalize it. So 255 and y 2. Actually, any of them could be, this is just an experiment, so any of them could be prediction tensor, and the other one will be the true tensor. cv2 dot imread. All right. Yeah, let's just print their shape, because I need to get a 4-dimensional tensor actually, because this method will be accepting only the 4-dimensional tensor. So print y pred dot shpe and also y true dot shape. Run this. All right, so this is my image shape, and we have a 3-dimensional tensor, so I need to reshape them. So my new y predict will be y pred dot reshape -1. The first dimension will be inferred, and the second dimension will be just as it is. Similarly, I have to do for the true. Reshape. Yep, makes sense. And now also check their shape. Yep, so now I have a 4-dimensional tensor. This additional first dimension was added with this code. All right, now I can check my dice coefficient. Dice will be equal to dice actually it will be dice score, dice coefficient, y true and y pred. Let's also print that. Oh, what happened? Okay, I did not run this method. Yeah, so that's my dice similarity, or dice, actually this is a coefficient, COEF. So that value is 0.480. So this dice coefficient is very similar to the IOU, that is intersection over union metric. They both are positively related, that is a dice coefficient and IOU are positively related, positively correlated, meaning if one says model A is better than model B at segmenting an image, that means then the other will also say the same. And like IOU, they both range from 0 to 1, with 1 signifying the greatest similarity between predicted and the truth. Oh, another thing, I just realized that I was doing this entire calculation on the int values, integer values, but in all projects actually you will be using float values. So you can convert this to float values by doing just putting 1 decimal after 2 here, where we are multiplying by 2, and also when we are normalizing to 55 dot and also to 55 dot. And that should work. Let's run all these again. Yep, I'm getting the same result. Yeah, so now I'm using the float values, because in real cases you will most certainly be using float values. That pretty much wraps up this very quick video. Thank you for watching. why do we scale the pixel values of the images in a neural network? Let's go over a very quick example to see if we do not do the scaling, what's the kind of effect we get. So in this example, I am using PyTorch to build a super simple neural network to predict the classification of my dataset, which is fashion MNIST. So initially, I'll go over the code very quickly because it's very, very simple, and I just want to show the result of the scaling here. I don't want to focus too much on the codes as such for this video. So first, all the regular imports, and I'm mainly importing PyTorch module and the Torch Vision because I'll be using the dataset of fashion MNIST for Torch Vision. So here is my dataset FMNIST. FMNIST is the name of the dataset, and I'm just here showing a random single image from that dataset. And here first the important class I'm building, which is dataset transformer, which will generate my dataset. And the important part to note here is that for the first iteration of this quick example, I am not scaling the data. So here is my input data X, and I'm just converting it to float, but I'm not scaling it. That is, I'm not dividing by 255, which is the highest value of a pixel, and which is normally used to scale the data. So in the first iteration, I'm not doing that. So without the scaling, otherwise these dataset transformer class, which generates my dataset, has a normal methods, that is init method, get item, and len. And then I am loading the data by using the data loader function of PyTorch. And then my quick and very simple model I'm defining here, that I have just linear layer, and then ReLU, rectified linear unit, and then the final is also linear layer. And that's my run model function, which will actually build the network. And then this function trainer, each batch is actually the training function, so which will make the prediction and which will calculate the loss and finally give me the loss for a particular batch. And this is another function, accuracy, which will be used for evaluating the model to calculate the accuracy of the prediction. And finally, in this cell, I am actually running the epochs, and for this example, I'm just running 5 epochs. And within the epochs, I am using the trainer function to train, and then the accuracy function to get the losses and accuracies. And finally, I am plotting the loss value versus epochs, and also the loss value versus accuracy. So for this first iteration, remember, the main key point is that I have not scaled the data. I have taken the raw input image in its original pixel value as it is, and fed the network, neural network, with the raw pixel values. And this is the result, kind of result I get. And remember, I'm also using a learning rate of 0.01, which I'm mentioning in my model here. So under the run model function, when I am applying this SGD, that is stochastic gradient descent optimizer, I'm using a learning rate of 0.01. And with this setting, this is the result I'm getting. So especially note the accuracy. So for the first epoch, I got an accuracy of 11%, which is like super bad. And then with the increasing number of epochs, my accuracy is actually improving. But after 5 epochs, my accuracy only improved up to something like 17.5% or maybe 18%, which is, even that number is super bad. This is no way acceptable for any kind of project or any kind of prediction. And now in the second iteration, I will make one single change, and that is I am going to scale my input data, and I can do that here just with a single line. So I'm commenting out, no, sorry, not here in my dataset generator function here. So I'm commenting out this line x equal to x.float. Instead, I am bringing in this line, that is, I'm converting the input x to float and also dividing by 255, and that will effectively scale the input pixel values, input images pixel values between the range of 0.1, and this is normally achieved by dividing all the pixel values by the largest pixel value, which is 255, and this is performed across all channels regardless of the actual range of pixel values that are present in the image. So with this single change, I'm going to run the entire notebook again. It will take only a couple of minutes to get executed. It took only kind of 1.5 minutes to get executed, and now see my final plot. See the huge changes in accuracy. Just with the single line change, that is scaling the data, I improved my accuracy to almost 86% here. Previously, it was like 18%, 1/8, when I was feeding the neural network the original pixel value without scaling. And with scaling, I improved my pixel values by such substantial amount. So this is just a quick example. Now another quick explanation of how these scaling affects what's the fundamental concepts and what's the kind of what's the mathematics behind it, due to which these scaling is affecting my prediction result. Now let's quickly go over the scaling concept and how this affects the activation function calculation and why scaling is so important in almost all neural network modeling. So first, note the sigmoid function values formula. It is 1 divided by 1 plus e to the power minus input into weight. And this weight remains the same whether I'm scaling or not, but this input value, this is what changing. If I'm scaling, it will be much smaller value, that is between 0 and 1, and if I'm not scaling, this input will be large value. So that's what I'm calculating in the table below. That on the left hand side, this is for non-scaled version of sigmoid value calculation, and on the right hand I have the scaled version of sigmoid value calculation. In both the table, the weight values remains the same. Only change is the input column. Here on the left side, I have taken the non-scaled version of the pixel value, and I have taken the maximum value of a pixel in an image, which is 255. And on the right table, I have taken the same input values but scaled. That is scaled by dividing the input pixel value by the number 255, giving me 1 for each of them. And now note the difference between how sigmoid is changing in values in the left table versus how sigmoid value is changing in the right table. So in the left table, we can see that when the weight values are more than 0.1, the sigmoid value does not change with an increasing weight value. Furthermore, the sigmoid value changed only by a very little when the weight was extremely small. The only way to change the sigmoid value is by having the weight change to a very, very, very small amount. However, on the right table, the sigmoid value considerably changed when the input value was small. The reason for this is this formula, sigmoid function, the calculation of this exponential and the mathematical implication of this. So the reason is that the exponential of a large negative value is very close to 0. And in the left hand side, our weight remains the same in both the calculation, but on the left table, our input is large. That means when I am doing this calculation, 1 plus e to the power minus input into weight, this expression becomes very close to 0. While the exponential value varies when the weight is multiplied by a scaled input on the right side of the table, because here the input value are all much smaller compared to these values on the left. Here input values are all between 0 and 1, and hence on the right table, that is when my input values are small and it is scaled, I am getting a more responsive sigmoid value changes. That is, here the sigmoid value changes when the weight changes, and that is more, these changes is more smooth during the whole calculation, because while the neural network layers will be back propagated and forward propagated and the weights will be updated, I will see a corresponding updates in the sigmoid value as well. Hence, scaling the input dataset so that it contains a much smaller range of values generally always helps in achieving a better model accuracy.